I think it's beneficial to talk about these two last questions from 5.2 before we get into 5.3 stuff. From geometry, we did a lot of this. I believe you do some of this in Algebra 2, dealing with angle of elevation, angle of depression type situations. But I do think it's important to maybe discuss these two questions in the concept in general. When you have situations where we want to measure maybe the height of something, but cannot physically measure it. For instance, this lady might, in this picture, might want to measure how tall or how high on the building that window washer is, but she doesn't have the ability to measure that vertical distance. And she doesn't have a tape measure. She doesn't have, a second person to help her, something like that. Okay, she can use some other calculation, some other values to find that exact height. All right, it all comes from right triangles and SOHCAHTOA essentially. But we get in the situation where they will provide us a distance away from an object, maybe. Okay, so they might tell you that she's, 30 feet away from the base of the building. Okay. Now, those are, you say, well, she didn't have a tape measure to measure the height. How's she got a tape measure to measure that distance? Well, you can walk that off, couldn't you? Okay, and get an approximation. And then they're going to give you the angle of elevation. They might say she has to, tilt her head at 30 degrees to see the window washer. Okay, and you might say, well, she doesn't have a tape measure. How does she have a tool to measure an angle of elevation? Okay, which is a valid argument. I don't know. Okay, she might have a theodolite on her. Okay, which is an instrument that's going to allow you to measure that angle. Or if you remember back to geometry, we talked about inclinometers. She might have one of those. It's just a protractor with an eyesight on it, basically. I don't know. I don't know how they're going to use, but we do these problems a lot. Okay. Sometimes you might see, if questions like they might say that you got like a telephone pole, and then you know what those wires off the side are called? Stabilized to the telephone poles. Cables. They are cables, but what kind of wire are they called? They're called guy wires. G-Y wires. Okay? But if I want to measure maybe the height of that telephone pole using knowledge about how far that thing is kind of driven into the ground from the telephone pole, is, obviously we can measure that distance right there, right? Tape measure, ruler, yardstick, measure it off, walk it off with my feet, whatever. But could I take maybe a piece of cardboard and lay that up against that wire on the ground here, and then trace out that angle? Does that make sense? Take that back, put a protractor on it, and now know that angle. Okay? So these are things that we can do. It might be a little bit more effort than them just saying, well, she knows the angle of elevation is 30 degrees. Okay? There's some probably work in developing that angle. But along with a line of sight, which is from her eyes, the observer's eyes, to the object, you develop a right triangle. Okay? And there are times that we're going to take some liberties in saying that, we're going to make the assumption that this building is going to be perpendicular to the ground. Okay? I'm not sure where I should really draw that. This picture is kind of maybe deceiving because they're trying to give you depth here and all that kind of stuff in 3 dimensions. So whether I draw the right angle there or should I draw it down here, I'm not sure. But you have this right triangle, and you should be able to then use SOHCAHTOA to determine that right triangle's values, the missing components. Does that make sense? We also have the situation, you can see it over here, they talk about an angle of depression. It's really the same thing as angle of elevation. Angle of depression just means you're looking down, right? Now when you look down, and this is the situation maybe that I want to talk about over here in this picture, maybe the observer is now the window washer, and he's looking down at the lady on the ground, okay? his angle of depression is right there. In order to do that, in order to develop that angle of depression, you have to add in a horizontal. Okay? And there's an infinite number of horizontals. Okay? So you think about this, take your horizon, and then take that horizon and start. Take that horizon and you start sliding it up, and all of those would be horizontals, right? Okay. The one that's going to be useful for us is the one that kind of meets at the line of sight. Okay. Creates that vertex at the point of line of sight here, and then we've got our angle of depression. Okay. But what we need to understand and realize is that if that's my angle of depression, that distance right there is called h. Is that the same as that distance right there? Okay. This distance right here is called d. Is that the same as that distance right there? All right. So this triangle right here is what in comparison to that red triangle? Careful. They're congruent. They're the same exact thing. Okay. So that's something to think about as we do some of these questions. And that's not, I mean, not every single question is going to need that angle of depression. Okay, the two we see today don't deal with at all with angles of depression. But these are two common types of questions that you're going to see throughout your homework. Looking at the exam that they sent out the other day for this first couple sections, first couple chapters, you see something similar to these two. So the giant redwood casts a shadow of 532 feet long. It says find the height of the tree at the angle of elevation of the sun is 25.7 degrees. So the tree is going to be a vertical distance, right? There's my tree. We're looking for the height of the tree, right? We don't know that. But we do know that it casts a shadow 532 feet. Right? Now the next question, we can look at several kind of different ways here. The way I like to think about it says find the height of the tree if the angle of elevation of the sun is 25.7. Okay? Whenever I'm getting one of these shadow questions, they're going to have to tell me, or I'm going to have to be interested in the angle of elevation of the sun. And the way I view that, or the way I think about that, it's an angle of elevation is from the line of sight, okay, to the object you're looking at, right? So the way I view it is that I've got somebody laying down at the tip of that shadow. So their eyeballs are right at the tip of the shadow. And they're looking at the top of this tree. And when they look at the top of that tree right there, that line of sight is going to take them right into the terrible sun. It's going to take them into the sun. Draw clouds. Does that make sense? Okay. Another way of talking about that angle of elevation, so that's 25.7 degrees right there. Another way that some people will discuss it and talk about it is they say, well, we put a horizontal right there at the tip of the tree, and that angle right there is the angle of elevation. Well, that should make sense to us, because if I were to just draw that line right there, in my line of sight, does anybody know what kind of angles those two angles are? Corresponding angles are congruent. Okay? So sometimes they'll talk about that angle of elevation for these shadow problems or sun problems as that angle right there. But we can transfer it right there as well. Okay? So the goal is then, can we figure out the height of the tree? Well, if we're making the assumption that the tree is perpendicular to the ground, we should be able to do this pretty easily, right? What components do we have here that we could use one of our trig ratios? Remember, our trig ratios are defined off of an angle, right? So you have to choose an angle first. Which angle you want to deal with here? You have all three angles, don't you? You have the 90-degree angle, you have the 25.7-degree angle, and you have the other one up there at top. You got to do a little bit of work to find it, right? So we can find it. You probably want to use the 25.7, right? So if I'm gonna focus on the 25.7, what side is this in regards to? Opposite. And what side is this? Adjacent. So which trig ratio you're going to use? Tangent of 25.7. Okay. Is equal to opposite, so h over 532, right? Multiply both sides by 532. 532 tangent 25.7 is equal to 8. Okay. Now, what kind of number is that? If I left it that way, is that exact or is that rounded? That's exact. Okay. And there will be times that we want to leave it that way. There might be times where we want to go a little bit further with this question and use h somewhere else. Okay, and do some calculations with h later again. And if I were to round h now and then do further calculations, that rounding error is compounded, right? And it makes those further calculations kind of incorrect. Okay, and we can maybe if we do want to round it, we can do some preliminary work. Say, okay, I want to minimize my rounding error. And you guys do that. You do that in science. You do percent errors and stuff like that, and try to figure out I want to be within this, plus or minus this percentage in regards to rounding error. We could do that. But what I want you guys to understand for the most part is that is a number. 532 times tangent 25.7 is a number. Tangent 25.7 is a symbol. This is a symbol for, I think it's like 0.4 something, maybe. Okay? If I multiply, or if I type in my calculator tangent 25.7, it's going to spit back another number that it's actually representing. Does that make sense? That number it's representing is an irrational number. So we cannot write the whole thing out accurately without rounding. So we write it as a symbol, like pi, right? Or like square root of 2. So tangent 25.7 representing another number. So I can leave it like that, implying the multiplication of 532 and whatever that other number is. If we wanted the rounded value, which is probably, maybe I'm a biologist and I'm tracking these trees and tracking their growth or whatever, I'm probably going to want to do something like this and get that number back there, 256.03 feet. That makes a little bit more sense, right? I can visualize that. I know how long that is or how big that is. Anybody get this answer? Let's see here. 338. That doesn't seem extremely obscure, does it? Okay. So we might go through this question and get 338.94 and I write that answer down. But what did I do before I typed that in? I put my mode back in the radians, right? Okay. So that's the thing. If you're not paying attention to your mode or in regards to degrees or radians, there will be situations where you think you are getting numbers that they kind of make sense. Okay. You got to be cautious. You got to always double check. If the problem is talking about degrees, my calculator needs to be in degrees. If my calculator isn't talking about degrees, then I need to put it in radians. Is that okay? People always ask, how do I know? Is there a degree symbol? And that tells you to be in degrees, right? Otherwise, put it in radians. Okay? Remember doing some of those questions? All right. Let's do this one here. It says from a point on the ground 500 feet from the base of the building. All right. From a point on the ground 500 feet from the base of the building. An observer finds the angle of elevation at the top of the building is 24 degrees. So we've got building here. Observer is 500 feet away. And our angle of elevation is going to be 24 degrees. So we're looking in this question to figure out it says find the height of the building and the length of the flagpole. So if you keep reading, they want that distance right there, so I'll call that H1. There's also this flag up there, right? And we want to know the height of that flag as well. And if you read it, it says the angle of elevation to the top of the flagpole is 27 degrees. So that's 27 degrees. Does that make sense? Okay. Now, we've essentially got two triangles here, and I'm going to redraw them for just kind of visualization reasons. If I've got my 24 degrees there's 500 feet. That would be H1, okay, which would be at the top of the building, right? There is also a 500 feet, so that number there is constant. The observer doesn't move, right? They don't move forwards or backwards when they're looking at the top of the flagpole. But they do have to tilt their head a little bit more to see the top of the flagpole or to get their line of sight aligned to the top of the flagpole. So that's 27 degrees. And this one we'll call it H2. Do you have the ability in those two triangles, those are both right triangles, do you have the ability to find H1 and H2 in both of them? Okay. So when I find H1, it's going to be the height of the building, which is the first part of the question. Okay. So which trig ratio would you use here? Yeah, use tangent again, so we're going to tangent of 24 is equal to H1 over 500. So we get 500 tangent 24 is equal to H1, right? So I'm going to type that in my calculator. Get the rounded value of that height would probably be appropriate here. And I can know the height of the building. Okay. Now, when I find H2 is from the base of the building to the top of the flagpole, right? So when I find that number, is that answering the question of find the length of the flagpole? Or is that asking find the height of the flagpole from the base of the ground to the top of the flagpole, right? That's finding that height. Okay? So I'm going to find that. I'm going to determine this length here, that distance. Okay? Well, what am I going to do with that distance eventually in that distance right there of H1? Yeah, I subtract them, and that's going to give me the height of the flagpole, the length of the flagpole. So when you do this, really the only component, these two triangles are the same, right? What is the only thing that changed? The angle. So when I find H2, it's going to be 500 tangent. Now the angle changed. Those are kind of little shortcuts that you can use once you understand this stuff real well. If you go through this type of problem several times, you find H1 using tangent. Deliberately then say tangent 27 is equal to H2 over 500. Multiply both sides by 500, and I get H2 to be 500 tangent 27. If I compare H2 and H1, the only thing that changed was the 24 went to the 27. Okay. So I can now take those two numbers and subtract them, right? Make sure I'm in the right mode. So we'll go 500 tangent 24 minus 500 tangent 27. Now, I've done something kind of deliberately here. When I hit enter, it's going to be a negative number. Okay? Because visually, think about my picture. Isn't H2 a bigger number? Or should be a bigger number? Okay? So when I type them in this way, I do get a negative number, but distance always has to be what? Odd. So when you're dealing with distance, it doesn't really matter the order that you subtract, and as long as you take the absolute value. Okay, so that's, I don't really care the order. I'm just going to take the positive version of whatever number I get back. So 32.14 feet would be the length of that flagpole. Is that all right? Okay. And then that's, it's skimming the surface, but that's some of the math that we use to determine measurements of things that we can't get to, things that we've never been to. We have a lot of information about the size of things on Mars, right? We're going to go there someday. Have we ever been there physically? No. And we send those rovers there. Those rovers they're not separating the two rotors, and one's got a tape measure and the other one holding it, and they measure things that way. They're using lasers and stuff like that, and pictures, and a lot of math to determine the heights and the distances of certain objects. Does that make sense? Okay. So that math is very, very, very important to us and very useful for us in measuring things that we can't necessarily get to. It's called indirect measurement. All right, so I think those will help you get through some of the story problems in that section. But I want to move into 5.3. We get about halfway through 5.3. This is another kind of set of skills that we're going to try to develop because we're going to use them over and over and over again throughout the year, the rest of the year. So this understanding is going to be very, very important for us as we move on. The idea here is that we're going to start taking these triangles that we were developing, and now we're going to force them to have basically what we'll call standard position. Okay, so we're going to take the vertex and we're going to force it to be at 0, 0. One of our vertices to be at 0, 0. And then the theta that we're interested in is going to be the angle that's created by the positive x-axis and our terminal red. Okay, so essentially the hypotenuse being the terminal red. We're interested in that red angle, okay, calling that theta. Now, the reason we do this is because our x and y axes are already set up and numbered according to the number line to allow us to find distances pretty easily, aren't they? Okay. If I know, let me just zoom in here real quick. If I know that I'm looking at this point right here, and I know the location of that point in the coordinate plane, that gives me, for theta, it gives me the opposite side real fast, and it gives me the adjacent side real fast, doesn't it? Okay? Because the x value of that point P is the adjacent side. The y value of that point P gives me the opposite side in regards to theta. Okay? And no matter where P is in the coordinate plane, and we'll talk, there are some special case scenarios, actually when P is on one of the axes. We'll talk about that later. But whenever point P is somewhere that is not the axis, you can always construct a right triangle. You can always, from P, go straight down to the x-axis to create a right triangle. Does that make sense? Okay. Now, the hypotenuse we're going to refer to as R. We'll talk about why here in a moment, why they call it R. But let's think about how we can determine what R is. Okay, it says let theta be an angle of standard position and let P be x comma y, a point on the terminal side. So that's the picture that I just showed you. Okay, it says if R is equal to the square root of x squared plus y squared. What is that? Where did they come up with that? Say again? That's the distance formula, but where does the distance formula come from? Pythagorean theorem. So if we look at this thing here, okay, that's x squared, right? That's y squared. We can call that r squared, right? A squared plus b squared equals c squared. Okay. Now Chris said distance formula, which is fine because that point right there is going to be some x comma 0, right? And that one there is 0 comma 0. Well, if I find the distance between those 2 points, x1, sorry, let's call it x2 minus x1 be x minus 0 squared, plus then this point here, okay, what we end up with, because this is going to be find the y distance, so I go y2 minus y1, so we go y minus 0 squared, and then the distance formula, well, what's x minus 0? X squared, that you just get x squared, right? What's y minus 0? Y squared, that I just get y squared, right? So it gives me r squared is equal to x squared plus y squared. So the argument that it's either the distance formula or the Pythagorean theorem is fine, because guess what you know about those two things? What's the relationship between the distance formula and the Pythagorean theorem? They are exactly the same thing. Okay, but we should be able to figure out that R if I know that point x y. I have all the components to find the R, right? Okay, so that should be really nice. Now, why do we call it R? And this is going to be a direct link to a lot of the stuff we do later on. And this is the link. You might have heard me back into geometry. I always get the question, we always talk about in geometry that triangles are kind of the foundation of every other shape, right? And I'll even say the triangles are directly linked to circles. And this is the reason. If I look at that R right there, okay, right now I've got that R. It's going to be, I think it's at 5 units. Okay, so it's 5 units long. That R is 5 units long. That R is 5 units long. All of these R's are 5 units long, so if I trace out all the infinite number of triangles that could be created with R being 5 units long, what do I get? Your circle, right? So R is the what of that circle? It's the radius, so that's why we use R. Okay? Now, eventually, what we're going to want to do is that we're going to want to take that R and reduce it to, let's see here. I don't know if I can do that. Point. There we go. Attach. Well, I can't do what I want to do. But we're going to, maybe I can. We're going to take that R and we're going to force it to be this length between A and D, which is now 1 unit, right? And everything that we learn about this big triangle, okay, can be learned from that little triangle right there, because they're both right triangles, aren't they? And they share a right angle, and they share that acute angle right there at A. So what we end up with, that tiny circle on the inside, we call that the unit circle. Whenever we have something with a measurement of 1, it's referred to as a unit whatever. Okay? You guys are in physics, right? You guys talk about unit vectors? Okay, they're just vectors of the length 1, right? Okay, that's why they're called that. This circle here, this big one, would not be a unit circle because it's got a length of 5 for its radius. But the idea is everything that we can learn about that triangle right there will tell us everything we need to know about this big triangle. Okay, and that's kind of the one of the main tasks of this course. All right, so we know that sine is just opposite over hypotenuse, right? But if I force this triangle to be in the coordinate plane, and I put it in standard position, opposite over hypotenuse now is just y over r, right? Okay. So instead of using the phrase SOHCAHTOA a lot of times, usually here you say sine theta is y over r. Okay. Well, here's what comes in to be really nice. If we can make r 1, make the unit circle, now sine of theta is just y, right? It's just the y value of that ordered pair, which is really, really, really nice. Okay. So that's the convenience of being able to condense everything down to that unit circle eventually. But cosine, it's adjacent divided by hypotenuse. Here you see adjacent is x and hypotenuse is r, so it's x over r. Okay. Now, there are no restrictions on r there. Okay. If you see the other 4 ratios, they're saying there's restrictions on the denominator, right? Well, if r were to 0, what's that tell you x and y were? They were 0 themselves, right? And if x and y are both 0, does my triangle exist? Okay. And logically, all r has to be, what we're dealing with there, x no matter where x is, whether it's in the first quadrant, second, third, fourth, you're going to square it so you get a positive number. No matter where y is, you're going to square it and you're going to get a positive number. So r always has to be a positive number, right? So there's no way, with the way we define things here, there's no way that r could be 0. Okay? But now, when I look at, tangent of theta equals y over x, okay, we could have a potential of division by 0, because let's say that p was right there. Does that give me an x value of 0? That makes sense? Okay. So, if you take on your calculator, type in on your calculator tangent of 90 degrees. See what it says back. Error, right? Okay. Undefined. Okay, because of this division by 0. Okay. And we'll talk about what, it's essentially at that point there is 0, comma, whatever I want my y to be. It's terrible. But y is any number I want it to be, right? Divided by 0, you get undefined values. Okay? So x cannot be 0 there. And we'll talk about that more in detail from different perspectives later on as well. But then you got those three trig ratios, and then the reciprocals should just be the reciprocals, right? Y over r is r over y, x over r is r over x, and y over x is reciprocal as x over y. Is that doable? Is this just the same thing as subtotal? Yeah. Knowing that opposite is your y value, adjacent is your x value, and hypotenuse is your r value. Okay. Now we can take and we can deal with our angle. Okay, so our angle that we're interested in is going to be, get back to this picture here. The angle theta that we're always interested in is the angle that starts with a ray at the terminal, the initial ray, that standard position, and then we're going to trace out and go to some terminal ray. So when I draw that, and I apologize. All right, so when I draw that back out, the angle that I'm actually interested in and that we're going to be talking about is going to be that angle right there. Okay? So let's say that I'm able to take that angle and make it, try to get to one there, close enough, 120 degrees. Okay? I'm interested in that 120 degree angle. It's really hard to deal with that 120 degree angle. Okay? There are better ways to deal with that 120 degree angle, and the better way is to find a point on this terminal ray. It doesn't matter where the point is. It could be B, it could be that point, it could be that point. It doesn't matter. But you're going to take from that terminal ray, and you're going to drop down a vertical line. Every single point in the coordinate plane, you can trace back a vertical line to the x-axis, right? Okay? And when I do that, that red line should be perpendicular to the x-axis, right? And now, in conjunction with that terminal side, that portion of the x-axis, do I have a red right triangle here? And what would this angle right here be? 60 degrees, right? Okay. Do you know a lot about triangles that have 60 degree angles in them? Okay. So what's nice here, if I want to know the sine of 120, or the cosine of 120, or the tangent of 120, it's a lot easier to ask the question, what is the sine, cosine, and tangent of 60? Okay? Because what I know about that red triangle is going to be the exact same thing that I learned about that 120 degree angle. Now, like I said, it doesn't matter where that point is. I could use that one. Is that green triangle still a 30, 60, 90 triangle? Yeah. And the hypotenuse of it is still that terminal ray. And then the same thing for maybe that little red triangle there. And eventually what we're going to do is, no matter what triangle we start with, we're going to condense it down to a triangle with a radius of 1. So maybe a lot of times we are going to be looking at that little red triangle eventually. But here's the question. If that's 60 degrees, okay, you know from 30, 60, 90 triangles, across from 60 degrees is always your n radical 3 side, right? Now, I don't know the lengths here. I actually do. Let's say, so R we said was 5, right? All right, so we said R was 5. So, that's going to be a pain in the butt. Let's just leave it as, across from 60, we know that to be n radical 3. You guys all agree with that? Something, you know? Okay. Across from 30 is always what? Careful. Across from 30 is always going to be your smallest side, right? Across from your smallest angle is always your smallest side. And then your hypotenuse is always your biggest side. Your hypotenuse is 2n. So our 2n would have been 5. So n would have been 5 halves, right? That's kind of ugly numbers. That's why I didn't want to deal with it. But if I ask you, what is the cosine of 120 degrees? Well, it's going to be a lot easier for us to determine the cosine of 60 degrees. What would be the cosine of 60 degrees here? What is the adjacent side to 60 here? N. And what's the hypotenuse? 2n. So when I say cosine of 60 degrees, it's n over 2n, right? Which is going to be 1 over 2, correct? Now here's the question. This n is that distance right there, right? Okay? And that is on what side of the x-axis? Is it on the positive side or is it on the negative side? The negative side. So this n should have a negative value with it, right? Okay? So that should have been negative. So that should have been negative, right? Okay? But what I'm telling you is that the cosine of this 120 is really what we're interested in. So our cosine of 120 should be the same as the cosine of 60. However, the x value is negative, and we get negative 1/2. So take your calculator out. Type in cosine of 120 on it. And you get negative 0.5, right? Negative 1/2. Okay? Or if you take cosine of 60, what's cosine of 60? Positive 1/2, right? And why is cosine of 60 positive 1/2? It's because if cosine of 60 is positive 1/2, because when I go to a 60-degree angle over here, your x value, would you agree this x value is positive? Would you agree that your hypotenuse is positive? So a positive divided by a positive is always a positive. If I came over here and I asked what is the sine of 60 degrees? Okay, so say that's 120. The sine of 60 degrees, well, this was n radical 3, and this is 2n, right? So opposite over hypotenuse is n radical 3 over 2n. So I get what? Radical 3 over 2? You get about 0.86 or something like that? Okay. So type in sine of 120, you get 0.866, right? Type in sine of 60. 0.866 again, right? Why? Why are they both positive in this case? Well, because no matter, R is always going to be positive, right? By definition, R is always going to be positive. Because R is found by taking this number and squaring it. Well, if I square any number, what kind of number do you get back? Positive. It's taking this number and squaring it. So I get another positive, right? What's a positive plus any other positive? Positive. And when you take a square root of a positive number, you get a positive number. So R is always a positive number. Well, an opposite divided by hypotenuse, an opposite is positive, hypotenuse is positive, that's got to be a positive value, right? So the sine value is always going to be positive in the second quadrant, where the cosine is negative in the second quadrant, because cosine is a negative divided by a positive in the second quadrant. Does that make sense? Okay. And this all comes down to SOHCAHTOA in understanding what the x-coordinate and the y-coordinate is of that triangle. Okay? Now, we use this so often that we've developed a mnemonic device to allow us to remember this a little bit easier. Now, this mnemonic device is just about the traditional, the three fundamental trig ratios, sine, cosine, and tangent. And then once you learn about those, should be true about their reciprocal, right? If I have cosine was equal to negative 1/2, well, wouldn't secant be equal to negative 2? So whatever the sine of cosine is, its reciprocal is the same sign. And whatever the sine of sine is, its reciprocal is the same sign. That's a pain in the butt to say. And talk about the sine of sine, right? Homophones, okay? So a lot of times when I say, I'll say like S-I-G-N sine. So I'll spell it out for you so you don't think I'm stuttering or whatever. But no matter where this triangle is in the first quadrant, no matter where I put it in the first quadrant, my x, my y, and my r are all positive numbers, right? And no matter what order you divide them, you're always going to get a quotient that's positive. So all your signs, S-I-G-N, are going to be positive in the first quadrant. Now, if my terminal ray ever ends in the second quadrant, okay? Meaning we're interested in that angle right there. That's theta. So what we're going to do is we're going to look at that triangle right there. And because my terminal ray ends in that quadrant, my x value would be negative, right? My x value would be negative. My y value would be positive. My r value would be positive. And as I do my division, any ratio that incorporates the x, or the adjacent side, would be negative, right? So cosine and tangent both incorporate that adjacent side. So you see then the negative functions are tangent and cosine, okay? Those two. As well as their reciprocals, right? Secant, cosine. Okay. Now if I'm in the third quadrant, everything except for r, so y is negative, x is negative, r is positive, okay? So anything that incorporates just one of those components, x or y divided by r, is going to give me a negative, right? So sine is going to be negative, cosine is going to be negative, but when I do tangent here, what's negative divided by negative? Positive. So we see that that's the reason why tangent is the only positive function in the third quadrant. And then we get similar relationships in the fourth quadrant. And then you guys can maybe work that out and understand those on your own. But what we develop here is this phrasing that all, and it's a mnemonic device, it's like PEMDAS or King Henry died by drinking chocolate milk, one of those things to help you remember something. All of your trig functions are positive. This is referring to the positive functions. All of them are positive in the first quadrant. Okay. Sine is the only one that's positive in the second quadrant. Okay. Now if I'm going to just sine, cosine, and tangent. Does that make sense? And then what you learn about the reciprocal should be the same as well. So sine and cosecant are positive in the second quadrant. We're going to write that. Tangent is the only one that's positive in the third quadrant, along with its reciprocal. And then cosine is the one that is positive in the fourth quadrant. And the phrase that we use is that going around from first to second to third to fourth, all students take calculus is what people kind of teach. I had a calculus student several years ago when I talked out. He didn't like that, and he liked to make fun of me. So he said all calculus teachers suck. You want to go that route, okay? But doesn't matter. Just develop something that you can remember. What are the signs, the SIGN, of those values? Because that becomes very important. You've all been in the situation where you've done an assignment. And I had an argument with a girl earlier, or late last week, I guess, in my geometry class. She got an answer of like 3, but it said -3 in the program. Are those the same number? No. So I can't say, oh, you just forgot the negative, right? That's because you could have done calculations that got the +3 legitimately. You did the wrong operation, the wrong process to get, just by coincidence, the opposite of what you should have gotten, right? So +3 and -3, they're not the same value. So when we go through this course and you get 1/2 and it should be negative 1/2, you are wrong. And it's not that you just forgot the negative. Does that make sense? Okay. So discrepancies like that, in the past, maybe I've been lenient, say, you just got negative here. That doesn't happen in trig, okay? Because the position is very, very important. Okay, first quadrant, second quadrant, third quadrant, fourth quadrant. We will talk tomorrow. We didn't get to it in this class. Tomorrow we'll talk about how we find cosine of 135. Okay, we draw the picture out and we really deal with a 45-degree angle instead of the 135-degree angle. What we like to do with angles that are really big, basically angles that are bigger than 90 degrees, we like to talk about smaller angles. And what we learn about those smaller angles tells us what we need to know about those bigger angles. Okay, so we'll start there tomorrow. There is a 5-3 that's due tomorrow. It's not due tomorrow. It's open, but I'll start moving that back at some point.